Yeah, welcome yet again to another class on differentiation. But in this particular case, unlike the other class where we were looking at derivation of simple terms or functions with simple terms, just single terms, we are going to look at derivation that combines several terms to form polynomials. All right, so. Basically, in mathematics, we define polynomials as any expression. Let's say we are using the variable x that take on the form of, in this particular case, let's use a as a coefficient. So we may have a, our coefficient there, and our value, our variable x there, raised to n. All right. So n can be any number from 0 to infinity, basically whole numbers. All right, they can also be negative sometimes, so basically whenever you are having several terms, forming an expression, then we say that is a polynomial. So we would have a, where a is a coefficient x raised to n, let's say, and then another term, after a x raised to n, basically a sum, would be, let's say, a1. All right, x, and then in this particular case, let's have our n raised to, okay, n minus 1. And we can go on. All right, we can go on and on, and to a point where, let's say, we are having a with, okay, of course, the value of the value of x being 0, the value of n in this particular case, that's the power of x here, being 0, because we all know that any number raised to 0 is equal to 1. So up to a point where we can already see that the power goes to nothing. So basically, in this particular case, a is a coefficient. When I talk of this particular form of expression, it becomes very difficult to understand unless I give an example. Maybe if I give an example of a polynomial, then it becomes easy to relate to it. So let me give a polynomial, let's say, of order 3. All right, a polynomial of order 3 would look like so. So an example of polynomials. Okay, so I'm going to begin with polynomial of order 3. Okay, so I'm going to give 2x cubed. So it is of order 3 because the power of x, the highest power of the highest power of x in this particular case happens to be 3. Okay, so that's why we're saying that it's a polynomial of order 3. So we have 2x cubed plus 4x squared. All right, minus 5x minus 7. All right, minus 7. This is an example of an order 3 polynomial. All right, so basically that is, in fact, without going any further, we can also use quadratic equations as polynomials. All right, quadratic equations can also form polynomials easily. For example, another example of polynomial, in this particular case, I want to use a quadratic expression. Okay, so this is a polynomial of order 2, basically. That is what this is going to look like. So I'm going to take polynomial 4x raised to 2. So it is a polynomial of order 2 because the highest power of x in this particular case happens to be 2. So 4x raised to 2 plus 3x, all right, plus 12. And I wanted to note that in these polynomials, the power of x reduces from the highest going on to 0. So in this particular case, the power of x is 3, the power of x is 2, so it's 3, 2, 1, and then 0 here. So basically, remember what I said, that any number raised to 0 equals to 1. So that is why we don't have to write x raised to 0 here. So we just have it as, we just have the coefficient of x raised to 0 there as 7, of course. So notice here as well, the polynomial reduces its power from 2, 1, so it's 2, 1, 0. Okay, so of course we don't show that here. All right, so we can also do the same with polynomial of order 4. Okay, polynomial of order 4. So a polynomial of order 4, you can already guess, will begin with the highest power of x being equal to 4. So we can take 3x raised to 4, and then we expect that the one that comes after that should be, as the power should be slightly lower, plus x cubed, all right, minus, in this particular case, it's minus x. So it could be that the coefficient of x raised to 2 is 0, or it could be that's why we're not saying that. But these are examples of polynomials, and in this particular class, we are going to mainly focus on how to find derivatives of such expressions. Okay, all right. Especially now that we already know how to differentiate terms. All right. So let us handle our first example, then move on from there. Awesome. So we're going to handle our first example, which is a derivative of a function s here. Function s, that is a distance function, basically showing the relationship between time and distance traveled. Okay, so anyways, let us not go into the details of the function. But so we're going to handle the derivative of s, which is a polynomial, all right, 2 t cubed minus 3t raised to 2 plus 4t. So this is an order 3 polynomial, all right? So it shouldn't be very difficult to handle. So one thing I'll say, that when you're handling derivatives of polynomial, what you want to do exactly is focus on finding the derivative of each term. All right, that's what you want to do. You want to focus on finding the derivative of each term. So we're going to treat each term as on its own. Then at the end of the day, write the all derivatives as an expression, the all derivative of the function as an expression. So the derivative of function s with respect to t, all right, ds dt. So we are deriving the function s with respect to t, as t is the variable, is a variable. Okay, the function is s, and the variables that we're trying to derive are made of t here. So as t is the variable there, so the function of s with respect to t in this particular case will be equal to naught. We are going to derive each term on its own. We're going to derive each term on its own. Will be equal to, first of all, beginning with the first term, it will be 3 times 2, which is 6. Okay, t 3 minus 1. Okay, 3 minus 1 will be 2. All right, so that is the first term we've derived. All right, note that's the first term we've derived. So the second term will be actually very easy. Minus, so 2 times 3. All right, it is the power of our variable t times the coefficient. All right, so 2 times negative 3 will be negative 6. So that will be negative 6. 2 minus 1. All right, 2 minus 1 will be t. And then in the last scenario, it will be the power here is 1, so it will be 1 times 4, and of course that will give us, all right, 4. And then note, it will be 1 minus 1, and because you see of course 1 minus 1 will give us 0, and I say that any variable raised to 0, any number raised to 0 will always be equal to 1. So in this case, because the variable that is t raised to 0 will be equal to 1, we won't write it. Okay, we'll just have because that will be 4 times 1, which is just 4. All right, so in that particular case, then our derived function of s will be 6t squared minus 60 plus 4. All right, and that is how we derive polynomials. Basically, we treat each term on, as individuals, and then we group them all up together as functions. Why don't we try another example and see where this leads to? Yeah, awesome. Example 2, we are having a polynomial or a function y, which basically is factorized. So it is x plus 2 into x minus 1, all right? and we are supposed to differentiate with respect to x, of course, all right, with respect to x, as x is what is the variable forming the function there. All right, so notice that we won't be able to differentiate this function as it is, because we're supposed to treat each term as, on its own, all right, on its own, as we're deriving it. So basically what we're going to do in order to differentiate this function, we're going to first of all have to expand, that is, remove the brackets that are in the function, the factorized function of y. So basically we're going to maintain one, the normal expansion method. So we're going to have x into main, that is, break one bracket, maintain the other. So it's going to be x into x minus 1 plus 2 into x minus 1. All right, so this is going to be x squared, x times x, all right, and then x times negative 1, that is going to be negative x. Then we're going to have 2 times x, and that's going to be 2x, and then 2 times negative 1, that's going to be negative 2. All right, so that is still not simplified. All right, so for us to simplify this further, we're going to have x squared. So negative x plus 2x is going to give us x minus 2. And so there we go. We are having an expanded version, an expanded form of our function, which we can then go ahead and differentiate. All right, or we can go ahead and find its derivative. All right, so the derivative of y in this particular case, all right, so the derivative of y with respect to x, that is dy dx, which I'm also going to introduce something else, which we can also write as y apostrophe. All right, y with apostrophe. So okay, so the first derivative of y apostrophe, because we can also go to an extent of having two derivatives of a number, of a function. So right, of a function. So we can first do the first derivative and the second derivative. Right, so the notations are very important for you to learn. So basically the derivative of y with respect to x, which we can also write as d, the first derivative, that is d raised to d apostrophe apostrophe y, that is not really d apostrophe, but y apostrophe. So anyways, the derivative of y with respect to x in this particular case will basically mean that we have 2 times the coefficient of x here, which happens to be 1. So 2 times 1 there will be 2. And then of course we'll have our x. 2 minus 1 will be 1. All right, so that is in this particular case. This term has already been derived for us. Then we go to the second term. We have our nth power there to be 1. So 1 times 1, which happens also to be the coefficient of this particular term, will be equal to 1. All right, 1 times 1 will be equal to 1. And now then 1 minus, oh, just a minute. Then 1 minus 1 will be equal to 1. So basically the derivative of x in this particular case will be 1. The derivative of x in this particular case will be 1, as we'll take the power 1 times 1. All right, and then of course remember it will be x raised to 0, which is just 1. All right, now in this particular case the derivative of any constant is always equal to 0. Okay, the derivative of any constant is always equal to 0. Why? Because we assume that in this particular case the x value, the x variable next to 2 is raised to 0. Okay, so 0 times 2 then becomes 0. All right, we always assume that. It's just that we've not written it, but we always assume that here we are having x raised to 0, so that when you take 0 times 2, we get 0. All right, so the derivative of any constant or any number or any coefficient, the derivative of any constant is always equal to 0. So in this particular case, the derivative of this particular function will be 2x plus 1. If you have any question around that, you can drop a comment in the comment section. Then we'll see maybe if you can be helped around that. Let's look at another example. Yeah, so this is the last example of this particular class, that is on derivatives of polynomials. So we're having a polynomial here, y equals to x cubed, which actually is an algebraic fraction. So it is y equals to x cubed plus x squared, all right, plus x, all right, y equals to x cubed plus x squared plus x all over x, all right. So whew, looking at this, you may feel scared, but it's nothing to be scared about, really. So for us to approach this particular problem, we want to write it such that all the terms are separated individually within the whole function. All right. So we don't want to write it as an algebraic function. We want to write the whole expression in with the terms being independent. Okay, with the terms being independent. So basically, what we're going to do here, we are going to, first of all, before anything, simplify the whole function. So we're going to have this here as y. Okay, so x. So basically, we're going to divide all the terms by x, all right, so that we do away with our LCM there, all right, our denominator right there. So we're going to have that x cubed divided by x will be x squared, plus x squared divided by x will be x, plus x divided by x will be equal to 1, plus x divided by x will be equal to 1. I hope that you are able to follow and that it's all making a little bit of sense. All right. So now that we have this in this particular format, it becomes then easy to then go ahead and solve the whole thing. All right. So basically, we are going to have to find the derivative of y with respect to x, okay, which I told you earlier on that could also be written as the first derivative of y. All right. So this is just a notation so that when you meet this maybe in any other book that you're studying, it's not confusing. All right. All right. Is going to be equal to. So we're going to take 2 times the coefficient of x there, which happens to be 1. So 2 times 1 will be equal to 2. Okay. And so that will be x. All right, and what will be the power in this particular case? It will be 2 minus 1, which will be equal to x, just as it is. All right, then we are going to have x, derive x. So we're going to have 1, which is the power of x in this particular case, times 1, which is the coefficient, and that will give us 1, all right? And then, of course, the power of x after this will be 1 minus 1, which happens to be 0. So a number raised to 0 equals to 1. So we don't have to write it here. A number raised to 0 equals to 1. So we don't have to write x raised to 0 in this, next to 1 there. So we can just leave a 1 as it is. Then I said earlier on that the derivative of any constant will always be equal to 0. Okay, the derivative of any constant will always be equal to 0. And why is that so? Because we assume that x in this particular scenario, that is in the function that has not yet been derived yet, pre-differentiated function, we assume that the power of x here actually is 0. So when you take 0 times 1, any number multiplied by 0 is 0. So that is why anytime you're trying to differentiate a constant, it will always be equal to 0. All right. So basically, the derived function of so dy with respect to x will basically be 2x plus 1 there. And so that is it for this class. If you have any questions, drop it in the comment section, and see you in the next one, and have a lovely day. Thank you.